Section 5.5 brings together several of the concepts we've been speaking about for the last couple of weeks. We're going to do a circuit example here, which is the point of section 5.5. It shows how we can take an arbitrary input, which we're going to be showing on the next slide, that's periodic, and figure out how a linear time invariant system, such as an electrical circuit, will affect it. Now, in section 2.7, we saw that for a complex exponential input, which was e to the plus j omega t, if we ran that through the convolution integral, we got a frequency-specific function called h of omega, which turned out to be the integral over all time of the impulse response times the time-reversed complex exponential. And that was the frequency response, or it's also called the transfer function of the system. Now, that can be used to find the output to input ratio in the phasor domain. So that is gives us another method to calculate this function h of omega, which we've shown more recently, which is you can take the impedance. Here we have the impedance of our output over our impedance of the entire circuit, and we simplified it a couple sections ago. And for this circuit, where the output is taken across the capacitor-inductor combination, so we would have j omega L plus 1 over j omega C would be the output impedance, the output side impedance, and we divided that by the total impedance, which was R plus that impedance, and we simplified the fraction, and we came up with this. So that is another way to get this ratio. Now, you want to choose the simplest method for any particular circuit. If you have the impulse response, calculating this integral may be the best way to get the h of omega response function. If it is an electric circuit and you have the impedances, doing a voltage divider or other approach to find it would make sense. If you have the Laplace transform, then you take the Laplace transform value and you replace s with j omega, and that will get you the transfer function h of omega. Notice when you replace s with j omega, what we're doing is we're setting the real part of s to 0. Remember, the real part is the damping coefficient. And for what we're doing now is we're focusing on steady state responses. This complex exponential here, and by Euler's formula, the corresponding sines and cosines at frequency omega, they go on forever. There is no transient portion, so they are not decaying, they are not growing. We will deal with transient responses and decaying and growing signals a bit later, but for now we're focusing on periodic signals that last forever. Okay, so now we have this response or transfer function for our circuit. Maybe we found it for an arbitrary circuit by taking this integral of the impulse response, or maybe we found it for other systems by knowing their behavior in the Laplace domain. All three of these methods, Laplace domain, impedance domain for a circuit, and taking this convolution-based integral of the impulse response, are used at various times when we are analyzing and designing signal processing systems. Okay, so now we have H, or what the system will do to an input. Now let's assign an input. For this example, we're going to use a half-wave rectified sinusoid, and this is available in the section 5, chapter 5 of your book, the table of Fourier series, and there is one given for this half-wave rectified sinusoid. Now we see here this has all three parts. There are no symmetries here that allow us to eliminate either the even or the odd components or the DC. We can see this half-wave rectified sinusoid has a DC component, which can be shown to be A, the amplitude over pi, and it is neither even nor odd. Since it is neither even nor odd after rectification, we expect it to have both sine components and cosine components, and indeed the Fourier series does. It turns out that there is just one sine component that is at the fundamental. We just have n equals 1 here, and it has amplitude a over 2. So that would be a half of this height, but then it would go down where the sinusoid is rectified and up here. So the cosine components, along with the DC component, are taking that very rough approximation, which with the sinusoid at half amplitude, and as we add these higher and higher frequency components, we converge to the half-wave rectified sinusoid, and we will be showing that in a minute. Okay, so how does this apply to signal analysis and system analysis? Well, if we want to figure out what the output is for this input, what we do is we have to look at all the frequencies present. So here are the n's. They are all the even n's plus n equals 1 due to the sine component. And we figure out the input voltage phasor. Most of the input voltage phasors are real. The DC phasor, A over pi, will always be real, and the cosine only components, which are all the even n's starting at 2, will be purely real, following this formula here. There is also a sine component, which is A over 2, and remember from the Fourier series, we have x of n is equal to A of n minus j b of n divided by 2. So we have the negative b component, A over 2, is what comes up in our phasor here. And then for each of the relevant omegas, for each which correspond to each of the n's that are present in the input signal, we calculate the value of h that we had on the previous slide. So we have h of omega. It is a complex number shown in this column in polar form, and it's also useful to see it in magnitude phase form. So we give it here as magnitude and degrees. Then for each of these, we calculate the output phasor, VO equals the corresponding H times V in. And what that does is we see here the DC component is blocked, it's times 0. It gives us the output phasor at each of these frequencies. So here we have one at negative 90 degrees of input, adding almost 70 degrees, so the phases add, and we have about minus 20 degrees in the output phasor with this magnitude. So each of these lines corresponds to an output term. If we look at this one right here, it would be magnitude 0.176, so on, cosine. And then we have at the frequency times time. The frequency is n omega naught. So here we have 1 omega naught, so just omega naught for this signal, t, minus plus the phase term, which is negative 20.6 degrees. And we would go through adding up all the terms that way to synthesize the overall system response. Let's take a look at what that looks like on the next slide. Here we have 7 plots for various values of n. The first 7 values that do not have a 0 input, and then the last graph sums up the series for these first terms of the Fourier series for the input and the output. First graph is for n equals 0, the DC portion. Here we have an input of just over 3 volts, but since it gets multiplied by, its phasor gets multiplied by h equals 0, there is no DC component in the output. So in the steady state, our circuit is blocking the DC, as we would expect due to the reactive elements. Then we have n equals 1, the fundamental here, and we see the input is 0.5 of a volt, and it's a sine wave, so that comes up to half the amplitude of the blue input. And the other components are going to build it up more fully. Now, we see the H value here when we plug in n equals 1, so omega is just equal to omega naught. The H value is 0.35, so that takes our amplitude down from 0.5 to about 0.18. And we see the phase value is, the phase shift is 69.4 degrees. So what that means is the output is coming 69.4 degrees earlier than the input. Now remember, this is steady state, so it does not mean the system is non-causal, but it does mean that the output can be best represented by a phase advance, but still the system is causal, so everything we're seeing is due to earlier inputs. We do this for all the n's where the input is non-zero, and here we have a phase advance of only 40 degrees. Here we have a phase delay at n equals 4 of 30 degrees, and we see the phase delay is increasing at the higher frequencies in this RLC circuit. The amplitudes of the blue inputs from that series for the rectified sine wave input are decreasing. We see here the first one is 0.5, and then it's about 0.2, a little less than 0.05, a little less than 0.02, about 0.01, and so on. So those are the amplitudes making up the components of the rectified input sine wave. When I add up all of these, I get a very good approximation of a half-wave rectified sine wave. Notice there's a little bit of oscillation here. Notice that it does not make a sharp discontinuity in the first derivative when it's hitting the 0 volt point. That's because we have not added infinite terms of the Fourier series. We've only gone up to 10, so we have a good approximation, but not a perfect approximation of these discontinuities and higher frequency components of the half-wave rectified sinusoid. Discontinuities, that is, jumps in value or changes in first or second or higher order derivatives, cannot be perfectly represented by a finite number of terms in the Fourier series. So we get closer and closer, but we never quite get there. Now, if we look at adding up all the outputs, we see the DC offset is gone, so we have positive and negative voltages in the offset that roughly balance, that exactly balance out because there is no DC component. And we see when the sine wave starts going up, we go up for a while, but then the response does start coming down and balances out here, as we can see when we add up all those components. So we have a bit of ringing or a bit of underdamping to this half-wave portion of the input. And we found that out by just adding up several components of the Fourier series. Please, as a next step, take a look at the MATLAB code that is posted that generates these graphs and describes in more detail and shows you how to use the Fourier series numerically to represent an input, to transform it through the H transfer function, component by component, to an output, and then how that component can be built, that the output can be built up from those components to figure out the overall system response.